Welcome to E-Pathshala lecture series in computer science. This course is on operating systems, and in today's class we learn about how communication happens in client server systems and what threads are and the uses of threads. So, the learning objectives of today's class. So, we learn how sockets are used for inter-process communication. We learn what is meant by remote procedure calls and what is meant by remote method invocation and how they are used for inter-process communication. And we will get introduced to the notion of a thread, and we will learn about the issues when multi-threaded programming is being done. So, first we learn about what sockets are. So, what is a socket? The sockets are used for inter-process communication when there are two processes which lie in two different systems. So, these two processes lying in two different machines, two remote machines, they can communicate among themselves using a socket. And these sockets will be created in both the machines. Say for example, if a client and a server are to communicate among themselves, a pair of sockets should be created both in the client as well as in the server. And what is this socket? A socket is a combination of an IP address and a port. We all know that each machine has got a corresponding IP address, that is the address by which the machine is widely known across the world. And you also have something called a port number. We will see what a port number is. And say you have a socket which is a combination of say 161.25.19.8 and 1625. This means that this 161.25.19.8 is the IP address of one machine and 1625 is the port which runs on that particular machine. And communication happens between this port on this machine, and very similarly the other machine will also have a similar IP address and a port number, and communication will happen between these two sockets. So, look at this diagram. Here you see that there is a machine pansy.unif.edu and the IP address of this machine is 128.59.21.14, and there is another machine which lies in some other place, and the name of the machine is mc1.cs.xyunif.edu, and it has got a corresponding IP address 128.119.245.93. And very similarly there is another cluster of machines which again has got a number of machines which have their own IP addresses. So, here we see that each machine has a corresponding IP address. So, each machine is understood or recognized worldwide using this IP address. And when you are doing socket programming with TCP, as I told you earlier, you need to have the IP address as well as a port number. So, what is the port number? So, if you look at this diagram, here you find that there is a client and there is a server, and there are a number of services that are running in the server. Say for example, in this server, there is a web server service that is being provided on port number 80 and another echo server service that is provided on port number 10. And both of these services are provided in the same machine. And whenever a client is requesting for service, it will have to specify the IP address as well as the port number corresponding to the service that it needs. So, here we see that the client places a service request to this machine. The machine is identified by the IP address 161.25.19.8 and the service that it is requesting for is on port number 80. Okay. So, when this request is being made, then looking at the port number, that corresponding service will be provided to the client. And it is also possible for the client to get the other service which is again provided by the same machine. So, the IP address is going to be the same because it is the same machine that provides the service, and the port number alone is changed. So, this port number is 10. So, when the request is seen by the server, it finds that the port number is 10 and understands that the service is echo and not the web service that is provided on port 80. So, it understands that the service should be done by this port number 10 and that is being provided back to the client. So, when socket programming is done with TCP, the client must first contact the server. So, there should be a server process that must first be running, and the server should have created already a socket that is a combination of the IP address and the port number, and it should be waiting for the client. And when the client is contacting the server, it should have created a local TCP socket that is nothing but an IP address and then the port number of the server process which it wants to contact. As we had seen earlier in the earlier example, we saw that it provides the IP address of the server as well as the required port number. It can be either 10 or 80 depending on what kind of service it needs. And then this client will establish a connection to the server. It will send a request to the server and it will establish a connection with the server. And now when this request is got by the server, it may get requests from multiple clients. So, the server which is running, which is providing service, it may provide service to a number of clients. And when many number of clients request the server at the same time, the server should be able to service the client properly, all the clients properly. So, what it does, whenever a request comes from a client, the server will create another new small server process which will take care of the communication with that particular client. And when the next client requests service, the server will create another process which will service the new client now, and so on. So, this helps the server to service multiple clients at a particular time. So, here is just an example which shows that there is a host X whose IP address is 146.86.5.20 is trying to communicate with a web server whose IP address is 161.25.19.8, and the service that the server is providing is running on this port called port number 80, and the client creates its own local port number 1625 which communicates with the server with this port number. And for certain services that run on the server which are common, like say for example, if there is a HTTP that is being running on the server, then the port number is always fixed and it is always 80, where these are called as well-known ports. That is, if there is a standard service that runs in the server, then the port number is fixed and then they are called as well-known ports. And if you want to write your own application which will run on the server and which will provide service to different clients, then you can have your own port number that is being assigned to that particular service, which need not be a well-known port, and these ports are called as ephemeral ports. And now we move on to the next topic, that is how inter-process communication is provided using remote procedure calls. So, this is mainly used in distributed systems. That is, you have a procedure that can run on a remote machine, and if you need the services of that procedure, then you can send a request to that procedure to that machine and get the execution done in that machine and get back the results. Say for example, you write a procedure, you need to execute a procedure which needs or which involves a lot of math operations. And if you have a remote machine which is capable of doing a number of math operations very quickly, and then you can use that particular machine for executing this math procedure. And you don't have to run the procedure in your machine or execute the procedure in your own local machine. You can send a request, you can just send a request to the server, to the remote machine, get the execution done there and come back here. Okay. And so, this remote procedure call, or it's also called as RPC, it abstracts procedure calls between processes on network systems. So, you have a system which is network, you have a number of machines which are connected over the network, and you have a number of processes that are running on different machines in the network, and those machines and those processes in the different machines can communicate using RPCs. So, when you have this RPC, how it actually works? In the case of RPCs, in the client machine, there will be something called stubs, or which are called the client side proxies, which will run in the client side machine. And these stubs are actually responsible for the communication with the server in the server side. So, what these stubs do is that they collect the input that needs to be sent to the remote procedure, and it will all pack them inside one packet and send it to the server machine. And this putting all packets or putting all input information into the packet is called marshalling. So, the client stub will get all information and will put all information into a packet and will send to the server. And what is this marshalling? Say you have, for example, you have a procedure, a remote procedure that finds the sum of two numbers, say for example. So, in the server you need to find the sum of two numbers, and in the client you need to provide the two numbers which as input, and that needs to be sent to the server. And these two numbers that are provided as input here in the client side should be sent or should be put into the packet or should be marshaled and sent to the server side. The problem here is that the data that is present in the client side may not be in a format that is acceptable by the server, or may not be in a format that can be sent over the network. Say for example, there are two kinds of representations called the big endian and the little endian representation. That is, in big endian, the most significant byte is placed in high memory address, and in little endian, the least significant byte is placed in high memory address. So, if the client follows big endian and if the server follows some other kind of representation, then what can be done? Or very similarly, if the client follows little endian and if the server follows a different kind of representation, then what needs to be done? So, what is done is that whatever be the kind of representation that is used in the client side, that is converted into an external data representation format or XDR format, and this is now sent over the network, and this is called actually marshalling, conversion into the format XDR format and putting it into a packet and sending to the other side. So, now I am talking about an addition procedure being happening in the remote machine, and the input parameters, say the numbers to be added, will be put into an appropriate format and sent over the network. And in the server side stub will receive this message, and it will unpack the marshal parameters and it will execute the procedure with the input parameters that it has got, and it will have to return back the information or the resultant to the client. So, here now you see how this RPC can be done between the client and the server. And when the client stub needs to send the parameters to the server side, it also needs to know the IP address of the server in which this particular procedure is running. And it also needs to know, say for example, if this addition procedure has to be executed, it needs to know on what port this particular procedure is running. So, it can find out from the server earlier that on what port this particular procedure is running. Say it knows the IP address of the server, but it does not know the port on which the required procedure is running, then it can get the information from the server. So, here in this example, we see that the user calls the kernel to send the RPC message to procedure X. So, X is the procedure that needs to be executed, and the user is asking the kernel to send this message to that procedure X. So, the kernel first does not know the port number on which this particular procedure X is running. So, what it does, it sends a message to a process called the matchmaker to get the port number. So, it sends, it know, and the thing that we need to understand here is that we need to know beforehand the port number of the matchmaker, because the matchmaker can be someone who knows about the port numbers or the different procedures that are running. So, we just need to know only the port number of the matchmaker. So, having known the port number of the matchmaker, this client will send a request to the matchmaker to get the address of or get the port number of this procedure X. So, the request goes and it will send back the reply. So, now the kernel will put this RPC message and send to this particular port P. So, this sends back the reply that the port is P, and now it knows that P is the port to which the request has to be sent to execute that particular procedure. So, the match now you get the response back, and the kernel will send the RPC, and the RPC daemon, which is listening to port P, will receive the message, and it will execute that message, and it will send back the reply back to the client. And the client kernel, when it receives the message, reply message from RPC, it will pass the reply message back to the user. So, this is how RPC works. And now we have a remote method invocation. This is nothing but this is very similar to what happens in Java, very similar to RPC, but it is something which is done in Java. So, it is a mechanism that is done in Java which is similar to RPCs, and this helps one Java program that runs on one machine to invoke or execute a method which is present in a remote machine, or it actually looks at this message, this execution as execution on remote objects. So, here you see there is one Java program that is running in one machine and another Java program that is running in another machine, or you have a remote object that is present in another machine. So, it can execute a remote method invocation on this remote object, and these two need not be two different machines, it can be two different virtual machines that are present in the same machine. So, because virtual machines are looked at very similar to having two different machines. So, in the case of remote method invocation, very similar to how you have a stub in RPC, you also have a client stub here in the client side. So, the client, when it invokes a remote object, this client stub is called, and the client stub will create something called a parcel and send it to the server. This is very similar to marshalling in the case of RPC and sending the information to the server, and here it is called a parcel. So, it creates a parcel and sends to the server, and the server side, in case of RPC we called it a server stub, but here we call it a skeleton. So, the skeleton for the remote object receives this, and the skeleton will unmarshal the parameters and it will invoke the required method, and after that the skeleton will marshal the return value, the resultant, into again another parcel and send back to the client. The client stub will receive this parcel, it will unmarshal the return value and pass it to the client. So, this is remote method invocation in Java, which is very similar to RPCs. Now, we learn about threads. So, these threads, they are called as lightweight processes. Okay. So, when you have a single process, you can have only one sequence of execution, and if you can divide a process into multiple parallel executions, or if you can divide a process into sub-processes which can run in parallel, then each of the sub-processes can be executed using a thread. So, a single process itself can have many number of threads. So, these threads are called as lightweight processes, and this thread will have a thread ID similar to how a process has a process ID. The thread has a thread ID. it has a thread ID, it has a program counter, a set of registers and a stack all for itself. But it will share the code section, the data section and other resources with the other threads of the same process. So, you can have a single process which can create a number of threads, and each of the threads will have its own thread ID, program counter, stack and register set, but all the threads of the same process will share the code section, the data section and the other resources, say for example files, etc. and so on. So, how threads are being used? We can understand it by using a multi-threaded server. I told you earlier that when you have a server which gets requests from a number of clients, it will create a number of sub-processes so that it can handle all the clients at a particular time or at the same time. Now, rather than creating multiple processes, what the multi-threaded server can do, is it can create multiple threads, and all the threads can run in parallel under the same single server process. So, here you look at how a single threaded and multi-threaded process can look like. So, here you have a single threaded process where you have all this core data, files, stack, registers, etc. and so on, and you have only a single thread of execution or a single sequence of execution. In a multi-threaded process, you have code, data and files which are common to all the threads, but each thread has got its own stack and registers and they can execute in parallel concurrently. So, when you look at threads, it has got a number of benefits. So, one is responsiveness. When you have a single process, the time at which you get back a response will not be quick compared to a thread, because in threads you have multiple threads running simultaneously and hence the response can be very quick. And then in the case of threads, you do not have to allocate resources for each thread independently. But if it is going to be, if all the threads are going to be different processes, then resources have to be allocated independently. But here in the case of threads, sharing of resources can happen. So, you can share the resources, all threads of a particular process can share the resources and hence it is economical and resource sharing is provided. And now, when you are looking at threads, there are two kinds of threads. One is user threads and the other is kernel threads. So, user threads are provided by a user level library, user level threads library, but the kernel will only have a single sequence of execution. And the examples of user level thread libraries are the P threads provided by POSIX and Win32 threads and Java threads. So, in the case of user threads, you have the thread support, the creation of threads, the deletion of threads and the synchronization, everything is managed by the library, the threads, by the thread library. But in the case of kernel threads, the threads creation, the thread scheduling, management, synchronization, everything is supported by the kernel. The kernel can handle multiple threads. And this kind of kernel thread support is available in Windows, XP, 2000, Solaris, in Linux, Mac OS X. So, now it is possible to have a combination of user level threads and kernel level threads. That is, you can have user level threads as well as kernel level threads in a particular machine. And when this kind of support is provided, you have different types of multi-threading models. So, we will see that one after the other. The first one is many-to-one multi-threading model. In many-to-one multi-threading model, many user level threads are mapped onto a single kernel thread. So, look at this diagram. So, you find that there are a number of user threads and all are being mapped onto a single kernel thread. So, here concurrency in the sense like even though all can execute in parallel or concurrently, but finally there is only one kernel thread which does the final execution. So, concurrency is limited in the case of many-to-one model. And if you look at this one-to-one model, for each user level thread, a kernel level thread has to be created. And each user level thread is mapped onto a kernel level thread. And hence, see here in this example, you see that there is a user level thread corresponding to each kernel level thread, and all these threads can execute concurrently. And hence, concurrent execution is better in the case of one-to-one model compared to the many-to-one model. And it's also possible to have a many-to-many model. That is, you can have a number of user level threads and you can have a number of kernel level threads. So, the number of kernel level threads will either be equal to the number of user level threads, or it can even be less than the number of user level threads. So, this kind of option, or having many-to-many model, it will allow the operating system to create a sufficient number of kernel threads. And so, you can see that you can have a number of user threads mapped onto a multiple kernel threads. So, here compared to the one-to-one model, here you can even have less number of kernel threads, but there is more than one kernel thread, but need not be equal to the number of user threads. So, scheduling has to be done between the user threads and the kernel threads. The mapping has to be done properly. So, these are different types of multi-threaded model. And this thread support for threads are provided by libraries, as I told you. So, these thread libraries, they provide the programmer with appropriate API for creating threads, for deleting threads, and for managing threads. So, for example, you have pthread create, which can be used for creating pthreads. And similarly, there are multiple other APIs which help in creating threads, for joining them, for deleting them, etc., and so on. Okay. So, the main ways of providing or implementing thread libraries is to have library entirely in the user space, or you can have a kernel level library which is supported by the operating system. So, as I told you, pthreads is an example of user level libraries, and this can either be provided as user level or as kernel level. And pthreads is common in Unix kind of operating systems. Now, having seen what threads are, we will also see what are the different issues that can come in threading. We will see each of these issues one after the other. So, first is having fork and exec in a threaded kind of environment. We all know that fork is used for creating a new process, and when a new process is created, the old process is copied to the new process. A new copy, an exactly similar copy is made for the new process. So, in the case of a thread, when a thread is creating a new process or thread is calling a fork, what should be done? Are you going to duplicate only this particular thread which is calling the fork, or are you going to duplicate all the threads which belong to the same process? So, both versions are available in the case of operating systems. So, depending on the options, you can either duplicate only the calling thread, or you can duplicate all the threads that belong to the same process. And similarly, exec. Exec is very similar to the original case. So, when any one of the thread calls exec, all the threads will be overwritten by whatever program is given as argument to the exec. And then cancelling threads. So, what is thread cancellation? It is nothing but terminating a thread before it has actually finished its execution. This can be done in two ways: asynchronous as well as deferred cancellation. In asynchronous, you do not wait for the thread, you just go terminate the thread immediately. So, the target thread is terminated immediately. But in deferred cancellation, the target thread is allowed to periodically check if it should be cancelled. So, here the thread itself will keep on checking whether it should be cancelled or not. But in the earlier case, in asynchronous, there is no say for the thread, it is just cancelled or terminated. And then you got something called thread pools. That is, rather than letting a process to create any number of threads, what is done is the number of threads that are created is limited. So, earlier beforehand, a number of thread is created and is kept in a pool where they await for working. So, whenever the service is needed, the process tries to look at this thread pool and then try to use that particular thread. Okay. So, because of this, the advantages, it is slightly faster to service a request because you do not have to wait for creating a new thread and so on. There is already an existing thread. So, you can make use of the thread properly. And the other is, you do not just go on creating many number of threads, the number of threads that can be created is bounded. So, we have seen the different issues that can arise in the case of multi-threading situations. And it is also possible to have thread specific data. Say for example, if one particular thread needs to have its own copy of data. In an example is in a transaction processing system, each transaction has got a unique ID. So, now when a thread is created for a particular transaction, that particular thread can have its own ID which need not be shared with the main process, because this unique ID is specific to only this particular thread. So, thread specific data can also be allowed. So, I will summarize whatever we had learnt in this class. We learned that sockets can be used for inter-process communication, and we saw that RPCs can be used to execute a remote procedure, and RMI is also used in Java for executing a remote method. And then we learnt about thread. Threads are lightweight process. They can be user level and kernel level threads, and there is support for both user and kernel level threads, which results in multi-threading models like many to many, one to one, one to many, etc. and so on. So, thank you.